Hello. All right. New feature from Zoom, right? Okay, so let's start it. And today we're gonna first have some really interesting exploration into the package, into the software PyTorch. So it's a machine learning framework that we commonly used. A lot of researchers and people in industry that use to implement machine learning models. Okay, so so I guess this is the first time that we have come across examples in PyTorch in this course, but you may have already have previous experiences, and that is good. So because last time we introduced the concept of computational graph, okay, it's a concept for the convenience of basically implementing machine learning models, and it's basically a way to decompose complex computation into simple steps. Okay, we can implement those small steps of computation into modules, and then we put them together into our complex models. And the previous class, we had examples basically as an experiment on paper, right? Something like very basic arithmetic functions that is shown here, right? So you can look at this. This is exactly the computation graph, the first computation graph we built. And now let's look at, if we use PyTorch, how do we implement such a work using PyTorch language? Okay, well, PyTorch is not a language; it's a software package written in Python primarily, but the backend is very implemented with very highly optimized lower level language like C or C++. Yeah. So let's see. If we want to implement this using some framework like PyTorch, how do we do that? Yeah. So different frameworks like PyTorch versus TensorFlow versus other frameworks, they use different terms and different underlying mechanisms to implement the computation graph. But I would say the computation graph is a pretty universal concept. Okay, that almost any kind of machine learning engines or machine learning frameworks use. So in PyTorch particularly, the mechanism that is used is called autograd. Okay, so the torch autograd is you can think of it as an engine to implement computation graph. So what its main function is to conduct automatic differentiation for you. It's like it returns the gradients, or it returns the partial derivatives for all the variables defined automatically, so that you don't need to manually compute all the gradients. Okay, so now let's look at the graph. It's the same graph that we used in the previous class, and we have three input variables, which is A and B and C. And in PyTorch, we need to use some variable called tensor. We need to define some three tensor variables, like in PyTorch, in Python. So here's the screenshot that I copied from a Jupyter notebook. So basically, you import the torch and you use torch.tensor. So tensor is the basic units in PyTorch to store data, to store parameters, and to store basically any kind of variables that need to be computed. Okay, so we put the values here: the 3 for A, 2 for B, and 5 for C, right? And one special argument here is that we explicitly let the requires gradient arguments to be true. So this requires grade means we ask those three variables to require gradients to be computed. Okay, so this is very useful grammar in PyTorch. Okay, so only in those variables that are that are set true for the required gradient arguments will have the gradients automatically computed in the graph. Otherwise, there will not be any gradients computed for these variables. Okay, so we can define the computation graph with one line of code. Okay, we can simply write the expression of the forward pass. Okay, we write this expression of how the output function j is computed. Okay, we don't need to draw lines or boxes in this programming language. We simply use the expression, the mathematical expression that j equals 2 times a times b plus c. So this is after this expression is executed, then PyTorch will automatically create a graph, but that graph is not visible to us. It exists in computer memory, and with that graph defined, then if we see print the value for j, then we can see that the output is already computed. Okay, because this expression is executed, and the values from the input to the output is immediately computed. Okay, and we can see also this gradient function, which is a multiply backwards. So we don't need to care about this right now because it's some functions that'll be used in the later backward style. There are kind of so yeah, it's a technically speaking, it's a 1-by-1 tensor because they're like these box brackets over there, and I think it's for the convenience of later computation, but I'm not sure. So the tensor comes with a dimension, default dimension, and actually there's no explicit differentiation between matrix versus vector or versus higher order matrices in PyTorch. So every data in PyTorch is like modeled by this, is wrapped by this tensor object. Everything basically that stored data can be think of as a tensor, and tensor comes with a dimension. But for our input here, we just give it a 1-by-1 dimension. Okay, yeah. So some of these concepts in PyTorch is not like strictly mapped to the math or linear algebras concepts that we are most familiar with. Okay, so let's see the next steps. Okay, so far we're just done with the definition of the graph, and we have done with the forward pass, which is computes all the forward computations. But one thing that we didn't say that is that we don't like define these intermediate variables. Yeah, so probably if we define u in PyTorch as a using the expression of a times b, we can also observe the value of u in the memory, right? But for this demo, we just want to show a very simple example of how the graph is executed. All right. So next, let's look at the interesting idea of gradients, okay, and the so-called backward style. So remember, what we have done previously is that we let the inputs of A to increase by very little step, by 0.1, right? So that it's 3.1, and we observe how the J changed, okay? So now things are a little bit different. Now let's go from the output to the input, okay? And we will let the output object to receive some gradients. Okay, so we will let the output to receive some external gradients that we defined with this tensor that has a value 1.0. Okay, so which is to also please notice that these external gradients, it is outside the graph. It is not part of the graph because there's no required gradients equals true. So the default value for the required gradient equals true. We'll set it to be false. Okay, so there's no gradients required for the external graph, or for the external gradients. Okay, so and we will feed the gradients, the external gradients, to the gradient arguments when we call backward function on J. So this backward function on J basically will trigger a chain of operations that computes all the gradients for all the variables within the graph. And in this example, we will compute the gradients for A and B and C. Okay. All right. So let's see the outputs. So after the backward execution, the backward function is executed, and if we observe, if we print the gradients for all the input variables again, we will see that these gradient variables, they are already automatically computed. Okay, so before we compute the backward style, the gradients object for those A, B, and C are not defined. It will be none. Okay, so only after the backward statement is executed, we will have the gradients available for A and B. So remember these values 4, 6, and 2. Okay, these are exactly the values that we computed in the previous lecture when we computed by manually. Okay, it's basically like, remember how we compute the gradients, the partial derivative with respect to A, which is the multiplication between these three quantities using the chain rule, right? Which is 4, which is exactly the 4 here. And the gradients with respect to B and C, they are exactly the values stored in the gradient property or gradient attributes. Okay, so it shows a very convenient usage for using PyTorch to construct a graph, and the graph will return the gradients with respect to each variables defined in this graph. All right. So another thing that I put here is that after one step of backward is done, a common practice is that we need to clear the gradients, like call this zero function to make all the gradients zero. Because if it's gradient descents that we are running, then we basically need to update the parameters and in one iteration, and in the next iteration we need to recompute the gradients. Okay, so we'll need to having those gradients variables like cleared, basically make them zeros. Otherwise, the gradients attributes will be accumulated. They will have gradients increasing and increasing, and usually that is not what we want here. All right, so let's look at, because last time we also introduced the structure of a neural network, a basic neural network. And we will look at this example in PyTorch as well. So before we introduce this network, this and the linear module, actually, if we think of the nature of a network, okay, so yeah, why not go back to the previous slides. So let's look at those nature of the neural network. Okay, so the layer, for example, of this hidden layer of the neural network is actually has two components, which is W1 and B1. And W1 in nature is just this matrix, right? It's a 4x3 matrix. It's 4 rows, right? Because it has 4 units from A1, A2, A3 to A4. And it has 3 columns because it has 3 inputs from X1 to X3. So that's why the dimension for W1 is 4x3, okay? And there's also a bias vector called B1, okay? So the formula that we use to compute each activation, each output for the units is that we take the matrix multiplication between the inputs X and the W plus the B's, right? Yeah, let's see the equations. Yeah, so given one instance, it is something like we need to, so that's for one neuron. Let's look at the whole example of all neurons. So the computation we need to do is to take the weights and times makes the computes the matrix multiplication with X and plus the B, right? So that is something we need to do for to compute the outputs. And also, well, here we use the sigmoid function as outputs. Okay, so let me see if I can find a shorter form. Yeah. Yeah. So actually, we can use this term. Okay. So for layer 1, it's Z1 equals W times X plus B, or more generally, the Z is the W times A plus B, okay? So actually the computation is here, this actually includes this matrix multiplication plus some bias, okay? And followed by an activation. So let's look at how this can be implemented in PyTorch, okay? But today in this example, we're not going to show with some, not going to implement with some activations. We're just going to implement the linear parts. Okay. Yeah. So one idea is that because the W, yeah, A40 is from the input, right? Is for the input layer. So if we got W, if we want to implement W with very primitive grammars in PyTorch, we can basically make W a tensor, right? A W tensor, and each values is like a W11, W12, have rows and columns, right? So, and each, so W can be a tensor, and then we can compute the dot product between that tensor with the input vectors. So, but that will make things a little little more like there's some more additional work to do. So basically in PyTorch, it has provided a more convenient way, which is this n-dot linear. Okay, this module is so often used. So we can like import this torch.nn first, and the common practice is to rename it as nn, which is for neural nets. Okay, and we can define the linear layer by simply telling it the size of my inputs. Okay, so this statement tells that I am going to implement some neural network like structure that has input size 4, that takes the input size in 4, and the output will be 3. Okay, so the complete grammar would be like we need to let the in features to be 4 and out features to be 3, and the bias is also default true, which means that this m will contain a bias variable. Okay, so having this statement executed, if we print m dot weight and m dot bias, it'll be printing some. It will print out some matrix-like structure, right? It's a tensor, but it has like 3 rows, 3 columns, and 4 rows. 3 rows and 4 columns, right? Because we let the input feature to be 4 and the output feature to be 3. Okay, and the parameter for the bias is also a 3-column, or you can say that there's it's a three-dimensional vectors. So yeah, really pretty cool grammar that you can implement a neural network with just one sentence. So let's further explore how these things can be executed. Right, we are more interested in using it to make to conduct computation. So actually, the previous weights that we see is a random number. A random number, like basically drawn from a uniform distribution between 0 and 1. So all these values, their magnitudes are limited by 1. So this is a common
practice. Ask real quick why some of them are negative and why some of them are positive.
Yeah, so
if they're between 0 and 1.
Yeah, okay, so sorry, yeah, so it's not between 0 and 1. It's drawn from some distribution. I guess it could be a normal distribution that has 0 as the mean value and 1 as the standard deviations.
Okay,
yeah.
Makes sense then. Thank you.
Yeah. So it's not from 0, 1. That's a good point, good fix. Okay. So because for computation, for training a model, it's reasonable to initialize all the parameters to 0, because we assume that we know nothing about the data. We need to start from a white paper, right? So now for the convenience of our experiments, we can actually reset the values for the weights. Like, so these weights can be accessed, the data within the weights can be accessed by these dot data attributes. And it's in nature, it's basically a tensor, right? So with these statements, we create some tensor that have some arbitrary values, that have some values that we want, from like 1 to 12, now reshaped into these 3x4 matrix. And then we copy these values into the weights dot data. And the bias, we also initialized with all ones. Okay, so these are just convenience for the next experiments, but it also shows that the dot module is just a wrapper. It just wraps all the tensor into its data. Okay, so having these values, now let's also prepare the next step. So we're gonna prepare first a single input data. Okay, so let's just use some random numbers. Say this torch.randn will generate random numbers from a normal distribution with a 0 as mean and 1 as standard deviations. And in this particular shape, right, we want 1x4 vector that each component, each element drawn from this random, drawn from this normal distribution. Okay, so the shape of x will be 1x4, and we can compute the outputs of the linear model by calling it. So the model M that we defined in the previous slide is actually a callable object, which means in the grammar of Python, we can like write a parenthesis after M, and we use X as inputs. The output returned by these calling statements will be the output that we want. And if we check the shape of the out, it'll be 1x3, which is exactly what we want. Okay, so one technical point that worth our notice is that our input is 1x4, right? We have this first dimension. So this first dimension within the grammar or within the convention of PyTorch is usually used to define the batch size. Okay, so this first dimension can have a bigger number. It can have 100. The first dimension can have 100 as its size. Okay, but in this case, we only have one element. The first dimension is of size 1. Okay, but it can be of higher size, higher values. And the output is 1x3. Okay, so this 1 also corresponds to this batch size here. So this 1 will match the one here. So, and if this one becomes 2, it also becomes 2. And that means we compute the forward computation for 2 examples. And in this case, we only have 1 example. Okay, and where the 3 is coming from, the computation between the weight. Okay, so the weight is a 4×3 tensor, and the input x is 1/4. So it basically eliminates these 4. Okay, and the result will be a 3. And also, you can think of the function of this model is to perform a linear transformation. Okay, the input dimension, it will transform any inputs that is a 4-dimensional vector into a 3-dimensional vector. Okay. So next slide, we're gonna show how the multiple data examples look like. Okay, so we can simply draw from like sample more random numbers. Okay, we can simply like create a 100×4 tensor that basically contains 100 examples, and each of them is a 4-dimensional vector. Okay, and if we supply this one as the inputs, and the outputs would be 100×3. Okay, so this will be the under the same mechanism of the previous slide. So what we are actually doing is that for each one of these 100 data points, we apply this 4×3 linear transformation onto the vector, and the result will be a 3-dimensional vector. And we have 100 of such 3-dimensional vectors. All right. Okay, so now lastly, let's look at how the computation is done if we want to check whether the computation is correct, if we want to manually check if the basic neural network computation is correct. Okay, so what we can do is to give some very naive inputs. Okay, we let x to be a 4-dimensional vectors that has all ones in it. Okay, and we will print the results of this model taken by feeding the x2 into the model. Okay, so remember the weight of our model is like this, is like 1, 2, 3, 4 to 12, and the input is all 1. Okay, and some bias is all 1, right? We initialize to all 1. So the result of this is that we need to first take the first row, right? Take the first row and compute the inner product with x. Okay, so it'll be 1 times 1 plus 1 times 2 plus 1 times 3 plus 1 times 4, which is 1 plus 2 plus 3 plus 4, which is 10, right? And we need to add this bias, which will return 11. Okay, so this is a correct computation, right? And also, the second row will need to do the same thing, which is 27 and 43 for the last elements. So we can actually manually check if this is case, like basically extract all the NumPy arrays from the tensor. Okay, so a NumPy array is a different object from a tensor. Okay, so because in NumPy it doesn't automatically compute gradients for you, only tensor does. So by copying out the data into those variables, these are just NumPy arrays. So it will not cause the TensorFlow. It will not cause the PyTorch to automatically compute compute the gradients for you. So what we actually do here is to manually compute each outputs for each row, right? The first output elements will be the inner product between the first row in weights and inputs plus the first bias, right? If you observe these outputs, and by making it, and also we can these 3 lines of code can be rewritten in a compact form by using this one, because x is all ones. Okay, and if we compare the manually computed outs with the original, with the out2 computed by the tensor or computed by the PyTorch, it'll be basically the same values. Okay, so it shows that frameworks like PyTorch are really convenient to use, and this is just the forward step. So after this, the second half of this lecture is done, we're gonna show that the backward computation, the backward propagation is actually more much harder to implement, and PyTorch also handles that automatically for us. Okay, so now let's stop the first part of this lecture.